The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we'll start today. Sorry, I have a bit of a sore throat, hoarse voice. I was talking a lot this weekend. Okay, also, today we're going to do transaction malleability, segregated witness, and I'm endorsing an ICO for the first time ever, publicly, and it's Anne's intermittent cookie offering. So if you guys want cookies, thanks, Anne. It's an airdrop, in that you just get them.
But you can also donate to St. Jude Children's
Oh, right.
Hospital.
Yeah. So yes, it's cool.
I'll also just be giving that.
Yeah. So my first ICO, I'm endorsing. Okay, so malleability. So malleability is the ability to deform under pressure for a material, right? And so Bitcoin is modeled off of gold, which is the most malleable metal. You can make gold leaf and stuff. So clearly, we need to design Bitcoin to be malleable, right? No, I'm joking. Okay, actually, in the context of cryptography, we're calling malleability when it's not super hard definition, but it started with ciphertext, where if you can modify a ciphertext and that modification will carry over into the plain text when it's decrypted. It also applies to sort of messages and signatures. In our case, signatures can be malleable, which means you can change the signature and it's still a valid signature. So, given a signature S1 on message M1, you modify the signature to S2, or usually like S prime, and it still signs the same message, it still validates as true. So when we were defining signatures, this wasn't really an attack we'd considered, right? There's still a signature, right? And you can't forge a signature, but you can, dot an I or something, and the signature is slightly different. You can't create one yourself, but given a valid signature, you can make a slightly different valid signature. That's how it works in Bitcoin, in the Bitcoin signing algorithm. But there's all sorts of different contexts where malleability exists in cryptography. And then part of it is, things still have to work for whatever definition. So if you malleate a signature and it no longer validates, well, that's sort of a trivial, sure, you can do that to any bunch of bytes. You can just flip some of them and the whole thing doesn't work anymore. That's easy. But it has, properties where it still works. So this leads to some weird stuff in Bitcoin where you can change a transaction and it's still valid. And that's generally not what you want, right? When you're signing, if you've got some kind of contract or some kind of payment and you write a check, you don't want someone to be able to modify the check and still be able to cash it, right? And this can be a problem. I don't really use checks much, but they draw the line, right? $100, and then they draw a line so someone doesn't write and 99 cents or something after. Not that that's the greatest attack ever, but or 100 and then someone puts $1,000 or so. I don't know. But it's sort of like that, where someone can change the thing you signed, can change the thing you are agreeing to after the fact, and it's still valid and does something you don't expect. Okay, so a review of the transaction format, which should be probably in people's minds if you were looking at the homework, the problem set. And one thing to focus on is that the outputs don't look like the inputs, right? These are fundamentally different things, right? The outputs specify a transaction ID and an index, the inputs, and then the outputs specify a script and an amount. There's another 4-byte field here that doesn't matter, but so basically you're spending from a transaction and a sort of row, and you're spending to just this arbitrary pub key. But you're not spending from a pub key, and you're not spending to a transaction, right? You don't identify your transaction itself here. So this is constantly, almost every website that shows blockchains gets this wrong. So if you look at blockchain.info is probably the most popular. And you just look at a transaction. Oh, they don't have it anymore. Okay, so you look at a block. And then you look at a transaction in the block. going? No, not yet. There we go. Okay, so you look at a transaction. Yeah, it shows, this address is sending to these two addresses. And blockchain info is particularly egregious in that there may actually be more than one input and two outputs in this transaction. No, just, right? They like hide change transactions. Anyway, so it looks like, hey, here, this address had some money in it and it sent it to these two addresses. And if I click, oh, where did this money come? Come from 18EECZ. And it shows, here's the Bitcoin address. And, oh, it's got multiple money, multiple transactions this address has been involved in. This is not how Bitcoin works, right? They are running their own database and sort of making up this view of the network, which is incorrect. Transactions don't send from an address. They send from another transaction's previous output. And this is very confusing because in the case, let's say in this transaction, right, there is what is this, 767 something, right? Let me copy it. So it says, yeah, it's coming from 18EE whatever. And if I click on it, I get 3 different transactions. There is a specific transaction that 18EE was involved in that is being spent from in this transaction. I can look it up because I have an actual full node. So if I say get raw transaction and I put it in here, and I can see, okay, it was spending from C838. It was spending from this transaction, not just an address. So it's really, I mean, if you're coming at this sort of new, it's like, okay, fine, why do you keep talking about this? But if you've been working on these things, a lot of people, myself included, for like 6 months, a year, I looked at these websites and I'm like, oh, this is how it works. And then 6 months in or something, looking at the code, I'm like, wait, huh? Like this code is wrong, but no, this is the Bitcoin code that actually is running. And so it's a weird thing to sort of get used to. Like, no, you're not spending from an address. You don't show the address at all when you spend from it. You spend from a specific output. Okay, so that leads to some weird issues. Specifically, what gets signed? So to some extent, you're signing the whole transaction, right? You want to sign everything. When you're saying, I'm sending money from here, I'm sending it to here, you want to like make sure that your signature covers the entire transaction so that people can't add stuff after and remove stuff. So you want to sign the inputs and outputs, but the inputs contain signatures, and you can't sign the signature, right? That doesn't make any sense. The signature is the thing you're putting on at the end. So it's sort of weird, right? You've got this document, and you have a little line at the bottom for the signature, but should the signatures be maybe a separate page that refers to the previous page? It's actually kind of a weird, confusing problem. So in practice, in Bitcoin, what Satoshi did in 2009, you take the whole transaction, but you remove the signature fields. You basically zero them out. Just put a 0 there. And then you sign that sort of signature-less transaction. And then you put that signature in after the fact, right? And so that means if you change any bit of the stuff that gets signed other than the signature will break, right? So does that make sense? Right, you sort of have these, you have these empty lines kind of, and the idea is you empty them out, you make them blank lines, and then you take that whole message, hash it, including the empty parts, and then paste in those signatures after if you signed. You don't empty out every line, the line that you're specifically putting the signature in. You actually put a different few bytes in there. Which leads to other problems that I can maybe mention if I have time. But so this seems okay, right? It's like, well, look, I can't sign the signatures, sure, but if you change any bit of the stuff I'm signing, the signatures now break. So this seems perfectly safe, right? No one can change the amounts I'm sending. No one can change where I'm sending it to. No one can change where I'm sending from, right? All these things get covered in my signature, so I'm good. Problem. The transaction ID, the way you refer to transactions, is the hash of the whole thing. The TXID does not zero out the signature fields. So the identity of the transaction itself, the way to point to and indicate where you're spending from, that includes the signatures. So that also seems like, well, that's okay, right? When I point to something, I'm indicating the whole transaction, the whole signed transaction. But the problem is that can change, right? The signature itself may be malleable. And in Bitcoin, it is. There's third-party malleability problems. So the simplest one was leading zeros, where all these things are numbers. You could say, okay, someone's got a signature. It's this big, long string of bytes. I'm just going to put zeros in the front. I'm going to put a 0 byte in the front of it. And that doesn't change the meaning, right? If someone says, I'm sending you, $1,000, and I put a 0 in front of the 1 and 1,000, well, it's still 1,000. However, for the purpose of a hash function, if you have a 0 byte in front, that changes the whole hash. And so they got rid of this pretty early. They sort of, made it so that you had to have the exact right number. You can't have any leading zeros. But the first one was just, I put a 0 in the front. The harder one is called low S, where part of the ECDSA signature scheme, I showed before that it's this curve that's symmetric about the y-axis, x-axis. Whether the thing you're indicating is on top of the curve or it's sort of reflection on the bottom, it's valid either way. So for any given signature, there's another signature that will be valid. You just sort of flip it, make it negative or positive. So now there's a standard, okay, you need to have high S, right? Low S signatures should be invalid. Both of these are really tricky because they're third-party malleability. Anyone can just listen on the network, see a transaction, change the signature, and in doing so, they will change the TXID, which is how all the software refers to transactions. So it looks like a new transaction to most of the software. And the transactions are still valid, the signatures are still valid, and you're not sure which one will get in. There's also first-party malleability, or in some cases, second-party if you're doing transactions with multiple people signing. So I'm not going to go back into the elliptic curve signature algorithms, but there is a nonce, right? There's randomness that you inject into the signing process. It's not deterministic. It's not that given a message and my private key, I always compute the same signature. No, that's not how it works. There are signature schemes like that, but in the case of the elliptic curve stuff that Bitcoin uses, you have to make up a random number to make each signature. And no one knows what that random number is, so you could make up different random numbers. You can make as many signatures as you want. So given a message and your private key, you can make whatever, arbitrary number of signatures that are all different signatures, but they're all valid signatures. There is a sort of standard for how to make them the right way, not randomly. It's basically take the hash of your private key and the message being signed, put them together, hash that, and use that as your random number, because then the idea is, well, it's got secret information in it as well as the message-specific information in it, so no one's going to be able to guess what it is. And it's still kind of message-dependent, so it'll change each time. So there is that, but that's something you can do. It's a really good idea because if you use a non-random K, if someone can guess K, or if your random number generator is broken, they can steal all your money. They can figure out your private key. But so you don't want to be dependent on generating randomness. A nice way to model it is, okay, have some initial event where you're putting in random numbers and you're storing them, and then from then on you want everything to be deterministic. Then you don't have to rely on random number generators. So it's a really good idea to use this, and I use it in my software. Most things use this kind of standard. However, you can't verify that anyone's actually using it. It's purely internal. It's a internal way for you to make your own signatures, but no one can actually. You can't prove. Can you prove? No. I'm not going to say you can't prove you're using it, but not in any reasonable fashion. So no one knows if you're doing it. So this is an attack where you can say, okay, I'm gonna make a whole bunch of different signatures. They're all gonna be valid, but that will mean I've got a whole bunch of different transactions that are doing the same thing. So maybe the question is, what does this really do? Does this really hurt? If someone, dots an I on your check, it's the same amount, it's going to the same place, sort of who cares, right? Outputs are the same, inputs it's pointing to are the same. It's just this sort of annoying thing. Okay, I tweaked it and I changed the TXID. No big deal? Well, in some ways, yeah, it's no big deal. But a lot of wallets didn't deal with this well. right? So let's say you're running a wallet, you make a transaction and you sign, and you broadcast transaction to D5CAC, and it never gets confirmed. And instead, someone out there flips a bit, changes your transaction to 9CBA3E, and that gets confirmed. And your wallet just says, yeah, this transaction you sent never got confirmed. There's wallets that did that. Most of them have fixed it by now. But if you're thinking of transaction IDs as the identity, TXID, this is the name of the transaction. I create it. I'm watching it to see when it gets confirmed. And I'm not looking for some malleated version. I'm just watching this thing that I created. Never gets in a block. Weird. And it's just stuck in the wallet. So there are definitely wallets. I think everyone's fixed it by now. But a couple of years ago, definitely wallets that would have these problems. It's a wallet problem, right? Your money got to the right place. You just need to sort of either delete stuff in your wallet or upgrade the software or tell it to somehow forget about this transaction and actually look on the blockchain for everything similar to your transaction. But it did do some damage. I think, so, I don't know, 2014, the Mt. Gox thing, where Mt. Gox got hacked, and lost all the money. They blamed transaction malleability, which was kind of interesting. There may have been an attack on Mt. Gox that used transaction malleability. The attack probably was this, which was, log into Mt. Gox, withdraw some coins, modify the TXID to this, and then it gets confirmed. You get your coins, and then log into Mt. Gox and say, hey, this never happened. My withdrawal didn't work. And then their system would automatically issue a new withdrawal transaction. And so you could just start taking all the money out. And your balance on the system. It's like, well, we keep trying to send you money and it keeps never getting confirmed. And so we keep making new ones. I don't know to what extent that actually happened. There's a lot of controversy. It couldn't have been the whole thing for Mt. Gox, definitely. There's still a lot of uncertainty about that. But it does show, it's indicative. If you write your own software and it's not accounting for these things, you may be losing money, right? When people say, hey, this didn't work, make a new one, and then you keep doing that and losing a ton of money. But that's pretty sloppy practices, I think. Another issue, if you're spending from a unconfirmed change output or an unconfirmed output. So you make a transaction, you send to two different outputs, you've got a TXID. And you're sending 5 coins to this person and 3 coins back to yourself. That 3 coins back to yourself output, you might want to use it again pretty quickly. Sometimes this happens. And so you've got a change output. That's from transaction 1, 7FEEC1. So you're going to now spend that change output. However, the TXID of transaction 1 changes. So you're saying where you're spending from is no longer valid. And this is a big problem because now you've signed a transaction that you think is going to be valid, but the money you thought you were spending sort of moves out from under you. And so that transaction is no longer valid. Right? TX2 is now invalid. It refers to something which can never be confirmed because there's a different transaction that's almost the same, but they're mutually exclusive that did get confirmed. Okay, so this is bad. It doesn't seem that bad, right? And so for years in Bitcoin, this was a problem that wallets dealt with, software, and people would oh yeah, you have to back up your keys, delete your whole database, and resync the blockchain, and then it'll find the right transactions. Kind of hacky workarounds like that, where it didn't happen too much. It wasn't a great attack, right? You can annoy people. You don't get any money. So it wasn't a huge deal, but it was annoying. But the idea is you could always resign, right? You've got your private keys. If the money you are receiving sort of shifts around and changes its location, well, it's still yours. You just need to resign. But what if you can't resign? So the case of multi-sig, where in most cases, when you're doing transactions, if you just have one key, it's just you, that's fine. In the case of multi-sig, usually you're all friends to some extent. And you're all in the same organization or multiple devices that you own. But you can have sort of adversarial multi-sig, where you're signing transactions with people who are, you're sort of cooperating with them, but you might not really trust them. Or they might be potentially attackers, things like that. You can definitely sort of extend your multi-sig model into that. And there could be multi-sig pre-signed transactions where, okay, we've got this 2 of 3 output address, this output that exists, and one of the 2 of 3 has pre-signed a transaction and hands it over to me, and then they disappear. And I say, oh, okay, well, I'm going to now sign my side. But if malleability occurs and the transaction ID changes, that signature is no longer valid. Right? It's signing something that's not there anymore. So this is very important in payment channels, Lightning Network stuff that I'll get to in a few days. And so it wasn't so much that malleability was like a showstopper bug and everyone was losing tons of money. It was that it was preventing kind of new cool things from happening. Because there were a lot of problems with, okay, I'm going to, let's make this construction where we put money into a multi-sig account and then I sign like a refund transaction that's got a lock time before I actually fund it and things like that, where you couldn't reliably do it because if either party modified their signature, they could break the whole thing. And they could have attacks where it's like, okay, we're doing something together. Oh, look, it got stuck. Well, both of our coins got stuck in this place. Now it's sort of a hostage situation. And you can say, well, I think I should get 1.5 and you should get 0.5. It's like, wait, we both put in 1. So there's attacks that could happen. And so this malleability was a problem for people trying to do new cool things. So how do you fix this? Any ideas? Non-malleable signatures. So the one we did for the first homework, right? Does anyone have an idea about why the Lamport signatures were non-malleable? Like from problem set 1. You guys did this, right? But yeah, they weren't, right? There's no randomness for one. I'm pretty sure if you flip any of the bits, it's not going to work. So Lamport signatures are an example where, yeah, it's non-malleable. You can't produce multiple different signatures on the same message. So that's good. The thing is, many useful signature schemes are malleable. So to just say, no, you have to use a non-malleable signature scheme, it's not a great answer to the question. RSA, I'm pretty sure there's some weird malleability stuff in RSA. ECDSA, a lot of the systems have randomness in there, and they're malleable. So an idea that I had, like 2014, that I was sort of going for was just don't sign your inputs at all. Only sign your outputs. So you don't actually specify where you're sending money from in your signature. You do have to still specify it in your transaction because people need to know. But you say, I'm only going to sign off on the outputs, right? The sort of endorsement of my inputs is implicit because the keys match, right? So I don't actually sign off on which key I'm sending from. To some extent, that's redundant, right? You know I'm sending from these inputs because the keys match up and the signature is valid for this key. I really like this idea still. I think it's really fun. You can do a lot of cool stuff with it. It's also dangerous. It allows signatures to be replayed, which is sort of one of the big points of having UTXOs. Because if you send 2 outputs, so you could send, I have address, address 1. I send two outputs. So I've got output 1, output 2. And this one has 5 coins, this one has 3 coins. And they're both the same address, both the same public key. And then I want to spend them. And if I use this sort of signature scheme where I don't actually sign which input I'm spending from, it can be used on either. So maybe I'm not aware of this 5 one yet, or it just hasn't happened yet, or I haven't seen it. And I say, yeah, I'm going to make a signature sending 3 coins over here. And then someone can malleate the transaction without touching the signature and point it over here. And the signature would apply to either. And then this is a really good deal for the miners because now I'm spending 5 coins and only outputting 3, and the miners get the 2 coins difference. And so that's pretty dangerous. And also, even if they're the same, I just say, hey, I'm sending 3 coins to you. And then as soon as the receiver sees this output, oh, it'll also work here. I'm going to take another 3 coins. So this is mitigated by not reusing addresses, but people reuse addresses. It's so it is dangerous. I think in the context of multisig, you can reliably say like, okay, we're not reusing addresses because these addresses are the combination of multiple people working together. But it would allow really cool things where you could sort of work backwards, compute a public key that you could prove no one knew the private key to, but you could still sign with it, and like really weird, crazy stuff. Anyway, this never got in. People were still talking about it a week or two ago, like, oh, we could do these cool things with it, but it's dangerous, and so it's like, we're not sure if it's worth it. Okay, any questions about this transaction malleability so far? Okay, so any ideas of what you actually do to fix malleability? Nobody? Okay, we'll find out in 1 minute. Segregated witness. I don't think it's a good name. Separate signatures would be a much easier to understand name. So Peter Wool, who is really good at Bitcoin and makes all these cool things, he's not the best at naming things. Makes lots of cool stuff, but just makes whatever weird technical name. So it's a pretty straightforward idea. The idea is when you're signing a transaction, you hash a bunch of data to sign, but you don't include the signatures in the data you're hashing to sign them, right? Because that wouldn't make any sense. You can't. Do the same thing when you're referring to transactions themselves as TXIDs. So in the exact same way that when you're signing, you hash the data without the signatures, when you're pointing to a transaction to say I'm spending from there, also don't include the signature data. Just take the hash of the signature take the hash of the data without the signatures. So yeah, you just sort of have this pointer to another, you've got a pointer to a previous input and you've got the outputs, but the signatures aren't in there. So the idea is the signature can change and the transaction ID doesn't. Okay, but what about backwards compatibility? So this is a great idea. Why not go for it? But how do you make it backwards compatible so that old software can still work with it? Right? It seems like, a soft fork is I'm adding new rules to the system, right? I'm putting further restrictions on. This seems like just a change, right? It seems like, look, I'm now defining something in a different way. I'm removing the signatures from the TXID. How do we make this not appear to be a hard fork? Hard fork's easy. You just say, look, we're changing the entire system. From now on, TXIDs don't have signatures. So any ideas how you do this in a backwards compatible way? Or just give up, hard fork? Yes?
You make sure that you're not adding restrictions that screw with history.
Right. So you can't change old transactions, but having both at the same time is tricky. The way you do it, so the idea is it would have been easier to just start off this way, right? If Satoshi had just started this way, it would have been great. He didn't think of it. It wasn't a super obvious thing that, so you can do it as a soft fork. The way you do it is you make new outputs which don't require any signatures at all, and then you just don't have any signatures. This seems kind of silly. Signatures are pretty important. Otherwise, any arbitrary person could just take all the money. But you redefine things in a way that new people know about and old people don't. So this is actually what a SegWit output looks like. The output script is just a 0 and then a pub key hash. And then the sig script, the field for a signature is just nothing. You just don't put a signature there. And then when you're running the stack, you end up with a pub key hash on the top of the stack, which is some number. And it's, the interpreter looks at a number that's non-zero as true, right? Like in C or things like that. And then the coins move. It's great. Someone was joking that you could potentially make this into a hard fork because what if the pub key hash was 0? And SegWit, you found the hash, you found a pub key that hashed to 0, and then you signed with it, and then SegWit would accept it, but old nodes wouldn't. Actually, that doesn't work, but it's sort of a... Anyway, so this, if you're running the regular Bitcoin software, you see this, and no signature, and you're like, yeah, this doesn't need a signature, right? It's just a hash. Like, I don't know what this is. Fine, the coins move. It, evaluates to true. But the new version of the software sort of adds a restriction to this kind of output. It says, look, if you see this, this is a template. This doesn't actually mean put a 0 on the stack and put a pub key hash on the stack. It means something else. Now it means this is a pub key hash and look for a signature. But look for a signature in a different place. Don't actually put it in the place you're supposed to put signatures. Put it in a new place. And don't tell the old software about this place. We add a new field to the transaction inputs. It's sort of in the inputs, but they put it at the end. It's kind of weird. Logically, it's in the input. It's the same, but like physically, it's not, which is silly. I didn't like that aspect of it. But the idea is there's this new field in the inputs called the witness field, and in cryptography, witness mathematics it sort of means signature in this case anyway. It's a little bit more general. But the old software never sees it. So the idea here's the old transaction format. You've got your TXID and index, 36-byte sort of pointer to what you're spending, and then a signature, which is 100 bytes. And then this stays the same. And the new TX format, the idea is, yeah, the signatures field's still there. You just leave it empty, right? So you're not putting any signature. It doesn't look like you need to put a signature to the old software. And then you have this, third thing, which is witness, which is the same as signature, basically. Slightly different format, and like technically they put them all together and put it at the end, which is kind of annoying, but anyway. Logically, this is how they do it. They make a new version of the transaction format. So the old version looks like empty signatures. The new version looks like, here's this useless empty signature field, and here's where the real signatures are. And you omit this to the old nodes. So when people ask for witness transactions, when people know about this new system, yeah, you give it to them. So they say, hey, yeah, I'm hip to this new SegWit thing. Give me a SegWit transaction. And you're like, okay, here's the witnesses at the end. But when they don't seem to know about this, and they're running older software, and they say, hey, just give me the transaction, you give it to them without the witness at all. It still looks valid to, either one looks valid, right? However, the new people, they know that if you see this, it does not mean push a 0, push a pub key hash. There's a new rule that, no, this is a template. This is SegWit. I need a signature, and I need it to be in the witness field. So if a new node gets a transaction without a witness that they know needs a witness, they will declare it invalid. But the old nodes won't be able to distinguish. They'll say, yeah, it looks like no signatures needed here. Okay. So you're sort of tricking the old software into accepting things they shouldn't actually accept in some cases, right? There may not be a valid signature that goes into the SegWit transaction, but old software will still think it's okay. So this is how you make it into a soft fork. It's kind of ugly, but yeah. Did you have a question? Yeah.
Yeah, is this done implicitly? So when the signature is 0, then you know that, or unless you SegWit.
No, because it's based on the output script. You could make a different output script that would have a signature, no signature requirement, and it would still work even with this new system. So it's just based on, we changed the definition of an output script. So have this sort of template. You can still do weird, like you could put without a 0 in front. You could put just a pub key hash. And that's not defined in SegWit. That's not defined anywhere. It would just be, okay, yeah, it evaluates to true without a signature. Anyone can spend it. And you could do that. That would have to be a non-SegWit transaction, right? The only way to use a SegWit transaction is to have this special format for the output script. Okay. Any other questions about network stuff? Yeah. So it's, and this solves malleability in a pretty good way, right? For the old software, the old nodes, well, they can't change the signature because there isn't one. There's nothing to malleate. And from the new node's perspective, yes, the signature can change, but that doesn't affect the transaction ID. Both old and new nodes still agree on the exact same transaction ID. The transaction ID does not include the witness field, right? So when you're calculating a transaction ID, you include all this for backwards. And if there's this actual signature there, that gets into the TXID. But if you're using empty signature and only using witness, then it doesn't get into the TX80 at all. So both old and new software agree. And that's important, because if they didn't, the Merkle roots would look wrong, right? You take all the TXIDs, put them into a Merkle root, put that in the header, and that's really important that everyone agrees on that. So they do work together. So that's cool. Yeah, so this is kind of interesting. You've got two different sort of, old version, new version, operating at the same time on the network. And they agree on a lot of stuff, but they also sort of disagree on some things, right? So they agree on outputs of the transactions, and they agree on which inputs there are, but they have a slightly different view of what these inputs are. Some of them think no signature is here. Some of them think, yeah, there's a signature here. That's weird. They don't agree on how things got spent. What are some other things that these two different classes of nodes would not agree on? Any ideas? So you understand like how they see different transactions. What are some other aspects that may be sort of interesting for this consensus system that we have different views on? I forget what I put. I put two things right now. Any hint? Biggest argument since 2010 in Bitcoin. What do these two different classes of nodes not agree on? Yeah.
Block size?
Well, the transaction size. Yeah. So they both see two different transactions. One of them sees it with these signatures. One of them sees it without. They don't agree on how big the transaction is. They agree on the TXID, right? They agree on where the money's going, where it's coming from, but they have completely different views of how big this transaction is in terms of number of bytes. So this is really interesting. For many, many years, since 2010, everyone's been arguing. And one of the big aspects of, if we want to increase the block size, that's a hard fork, right? Everyone up to now, we're enforcing the block size must be 1 million bytes or less. There's no way around that, right? You can't just increase it. We've got this rule. You're breaking that rule. This is a sneaky way to break the rule, but still not tell people you're breaking the rule, right? Say, okay, I'm enforcing a rule that there's 1 million bytes. As far as I'm concerned, there are less than 1 million bytes in this set of transactions. The new nodes know, yeah, there's more than 1 million. There's like 2 million bytes in here. We just didn't tell the people who, we didn't tell the old software about all these extra bytes. So this is kind of an interesting thing you can do. So you can increase the transaction size without telling the old nodes. So, yeah, the old nodes don't see the 100-something bytes with the pub key signature. So they see transactions that are much smaller, around half the size, depends, but half the size-ish. So those bytes, they won't count those bytes towards the 1 million byte block size limit. So this ends up being a soft fork that allows you to increase the block size. In a kind of sneaky way, right? The old nodes don't think the block size is increased. They think it's less than a megabyte. And they also think, this is weird, I haven't seen any signatures for a while. Everyone seems to be using these transactions that don't require signatures, and somehow everyone's getting along and not stealing each other's money despite the lack of a need for signatures. But, these are not intelligent people. These are software programs, and if it'll just run and it'll, okay, yep, this evaluates the true. So it's kind of cool. Block size increase soft fork. However, you institute a new rule with SegWit. You don't want to just say, we don't count, for the new rules, we don't count signatures towards the 1 megabyte limit, right? You could do that, but then people might spam signatures, right? Let me make a giant signature or some kind of like 50 out of a million pub keys thing and spam the network. And then it will still be under a megabyte of non-witness data. So yes, now you've got two classes of data. You've got all the data that everyone sees and all the witness data that only the new nodes see. So what they did is they said, okay, the witness data still counts towards that limit, but each witness byte counts as a fourth of a regular byte. Okay, kind of weird, but yeah. So in practice in the software, what they do is they say, okay, we multiply the non-witness bytes by 4. So every output, every byte in the outputs and every byte in the like TXID input things counts as like 4 bytes. And then the witnesses just count as 1 regular byte. And then we now say, okay, the new block size is 4 million bytes. they don't, 4 million weight units, because they're sort of, okay, we've sort of got different weights for things. This actually makes sense because the UTXO set is what you really want to minimize, right? That database we keep updating every block. And the signatures don't go into the UTXO set, right? So the signatures you don't actually have to store on like a fast, low latency storage. So in a very real sense, the signatures are sort of okay to make bigger. They don't really cost as much to the network to store. So having this discount where you say, okay, the signatures, you can have a bunch of them. It doesn't really count as much. But the outputs, we really need to minimize. So this 1/4 is like somewhat arbitrary, but there are some calculations. They're like a little hand wavy, but it's like, yeah, this is about what it should be, to sort of try to balance things. Okay, so the end result, if you've got this discount, you can put about 80% more transactions in a block. You get about 1.8 megs. It depends, right? It depends how big your signatures are. So the maximum would be you have a block that has one transaction with just a giant signature that's like almost 4 megabytes. And the old software would see this block as being really tiny, like 100 something bytes. And the new software would see, oh yeah, this block is almost 4 megabytes. But that's sort of the extreme case. I remember generating some like 3.7 meg transactions to blocks on testnet a while ago, just to test it out. It works, but in practice, you're seeing about this. And in practice today, as SegWit has been, seeing more adoption, you see like 1.3 megabyte blocks. Not everyone's using it. The idea is it's backwards compatible. You can still use your old software, but it seems like more and more software is using this. You get a discount on your fees because your transaction seems to be smaller, right? You can fit more of them in a block. So it's kind of cool. And that's sort of an incentive to use it. Okay, other thing you can do. You can commit to signatures. This is a little tricky. If the signatures aren't in the transaction ID, then they aren't in the Merkle root, right? So there's nothing really committing the signatures into the blockchain. And this would actually work. You could say, no, I have a signature, I'll give it to you. But it could change, right? It could be malleated. So it could be weird though, right? You could agree on a UTXO set, but you could disagree on how exactly you got there. So one example would be multisig, where there's 2 of 3 multisig, Alice, Bob, and Carol. 2 of them need to sign. And then on my computer, it says that Alice and Bob signed. And on your computer, it says that Alice and Carol signed. That's weird, right? Like we're not, for accountability, if we want to know who exactly endorsed these things, we might disagree on it. There would be no canonical, like, here's the blockchain, here's who signed. The transactions themselves would all still be the same, but not the signatures. So that's kind of weird, but it also seems that, well, maybe that's part of the price you pay for fixing malleability in this way, right? If we're not putting the signatures into the like sort of thing that gets committed to in the blockchain, then yeah, signatures can change. So any way around this? It sort of seems like, yeah, that's the trade-off, right? Sneaky way around it? Sneaky fun? No. You know. Yeah. Okay, so what you do actually, you commit the signatures, but in a weird way. Okay, so here's the regular old Merkle tree, right? This is the Merkle root that you put in the header. Here's all the transaction IDs. And so you make these intermediate hashes. This is the hash of these 2 things concatenated together. This is the hash of these 2 things concatenated together. Now, if the TXIDs don't have signatures, yeah, there's no commitment to the signatures in the top hash. What you do is this. You say, okay, I'm going to make these new witness TXIDs, hashes of transactions that do include the signatures. In practice, you could just make a hash of just the signatures. That would also work. They just take the whole thing. And now I've got this sort of like other reflected Merkle tree kind of thing where, okay, I take the hash of these 2 witness transaction IDs, put it here, and this one just drops down. It's another Merkle tree. And then you get a root for all those things. We call it the witness root. And then what you do is you put the witness root in the Coinbase transaction. Put it in an op return. And the idea is the Coinbase transaction doesn't have any signatures anyway, right? So you can put it in there. you don't need to include the transaction 0 in this witness tree. Wait, they do though, right? But they like say that, no, maybe this is slightly inaccurate in that I think they actually do make a witness TXID for the Coinbase transaction, but they define it as being 0 or something. I think, I don't remember. So it's like weird, right? But you could do that. They define it as 0, or they let you pick anything you want. I'd have to look at the code. But anyway, the basic idea is, for these anyway, you take the hash of the whole thing, including the signatures, put it in the witness root, put the witness root in the Coinbase transaction, and the Coinbase transaction gets into the Merkle root. So you are committing to all the signatures, but on the block level, not the transaction level, right? So you don't. So in the case where I think Alice and Bob signed, oh, I think Alice and Carol signed, you can have those two transactions floating around on the network, and we can, they have the same TXID, and so who knows which one's getting it into a block? They look almost the same. Some of the software won't be able to pick between them. However, once it gets into a block, one of them will be committed to. And it's like, oh, it ended up being Alice and Carol that actually, those two signatures actually got into the blockchain. However, you could then, you could prove, hey, no, I had this Alice Bob signature, but then it never got into the blockchain, and maybe you made it after the fact. It never gets committed to.
Also, a bunch of pool software just doesn't bother to do this.
A bunch of pool software doesn't do this? What do you mean?
Well, it's the responsibility of the pool server to make this construction and put it in a Coinbase transaction, and a lot of people just
Haven't implemented, as in they just don't support SegWit? Or?
No, so they do the first part, and they don't do this one. So they signal SegWit support, and they just don't.
Okay, wait, wouldn't that just not work? Right, how?
Because to the old software, it just looks like.
But to the new software, if you don't have, so for one of, what just happened? Uh-oh. Okay, cool. You can touch it. Wait. When one of the rules in SegWit is a soft fork, right? You say, okay, we define these new transaction types. We define this sort of template where if you have a 0 and then this pub key hash. It also says, I require every Coinbase transaction, I require the Coinbase transaction to have this output that says op return AA9C, whatever, this little random, 4 random bytes, and then I require it to have the witness root in here.
Yeah, I'm guessing they just don't include SegWit transactions.
Yeah, so I've seen that a lot. Yeah, so a lot of the software says, I'm not going to do this. If I see a SegWit, so the other thing that's nice, SegWit transactions to old software look non-standard. So I mentioned before that there's, standardness rules where this looks weird. I'm not going to mine it. I'm not going to relay it to my peers. But if I see it in a block, well, okay, fine. So SegWit transactions look very non-standard, right? It looks like there's no signature. That's weird. There's this 0, like, what's going on? So yeah, you can still run a miner and just not even know about SegWit. It's a little dangerous because you might see a block that is SegWit invalid, but you wouldn't know it, and so you might try to mine on top of it. So there are some risks, but in general, if most people are doing the right thing, you could still mine without knowing about this stuff. So, okay, any questions about committing to the signatures? What else? Oh yeah, so you got this upgrade path. That's kind of cool. So it defined 0 pub key hash as, hey, this is now paid a pub key hash, right? Interpret this weird template as the regular, hey, verify this signature. I also, when SegWit soft fork happened, redefined a whole bunch of other templates like this. So, 1 and then some data, or 2 and then some data. Just put a number and then put a bunch of data. All of these are sort of defined as future upgrades. So if you see a 3 block of data, you now say, yeah, okay, I know that's SegWit version 3. My software will maybe pop up something, say, hey, people are using SegWit version 3. You're only aware of SegWit version 0. And you'll consider it non-standard. You won't relay it. But if it's in a block, yeah, sure. And you don't require anything about the signature. You'll just say, yeah, whatever weird witness data you provide for these outputs, I don't know how to interpret them. I'm just going to let it all go through. What that means is there's no witness needed. If a witness is provided, you just ignore it and you just think everything's fine. This allows easier upgrades. You have 16 new versions to upgrade to. Yeah, you don't require any specific things about this. So you can make new scripts. You can make a completely different script interpreter. You could say, okay, we're going to port EVM to Bitcoin and I don't know, disable some of the opcodes that don't apply, and have that kind of thing. Have new smart contracts. So it's kind of a fun we will and it's a nice easy upgrade path. You could have multiple different things like that. The code will be easier. You could do it. Don't do it today, right? You could construct an output that's a 2 byte and then your pub key, and send it out there. It will be probably stealable by miners, right? Because everyone else's node will say, "Yeah, I don't know how to interpret this yet. There's no rules about this yet." Okay, let me show you some SegWit stuff I looked for. You can see this, right? Okay, so there's actually like nested SegWit. I don't know if I want to. There's like an ugly I don't want to describe it. I didn't like it, but yeah. So this is like somewhat designed by committee E. There's also this is like 2016, right?
People lose so much money. So
yeah. So the other thing I was saying with this, I was like, okay, you've got this witness to EXID, and I remember people working on SegWit, and I said, hey, why don't you make the transaction IDs a Merkle tree of the inputs and outputs instead of just the hash of everything altogether? Then if you had a really big transaction, you could prove that an input had been spent without sending the whole transaction over. And I thought that was a cool idea. And then when I talked to people, they're like, yeah, Peter Todd already said that 3 weeks ago. And whatever, we're not going to do it. It's too late. We already coded stuff. Oh well. And that's the sort of fundamental aspect of SegWit. You can't really upgrade that in the new script versions. So, whatever. There's also still a hard rule on transactions themselves being less than a megabyte, I think. So it's not a huge deal, but it would have been cool. Another thing is there's actually a way. So there's no address defined for this, right? Addresses map to output scripts in all the software. And so when you say, okay, I'm sending to 1AEECC or whatever, it knows how to interpret that address, build the 20-byte pub key hash script, and send to it. And vice versa, right? So from the address, you can get this output script, and from the output script, you can get an address. So when a old software sees this, it's just like, there's no address. I don't even know what that is. I've never seen that. And so people worried that oh, it's going to be weird. People are going to have to upgrade to even send to people using SegWit, right? So it's backwards compatible, but if you want to say, hey, send me some money at this SegWit address, and then they can't. And so you say, okay, fine, send me the money with a regular address, and then we still have this malleability problem, and then I have a wallet that supports both, and I can move money to my own addresses, and it's kind of ugly. So they made this nested address thing, which I don't like, because then it has both. So you've got a signature and a witness. And the signature is not a real signature, it's just pointing to the witness. It's really ugly. There's a bunch of weird stuff in the SegWit code that not super into. I don't have to use it though, right? That's the beauty of these permissionless innovation kind of systems. Ooh, I don't like that code. Okay, I'm not supporting it. So, yeah, okay, so, whoa, what just happened? Whoa, I didn't know you could do that. Okay. Okay, so here's one that's nested. So I would just randomly looking through a block. Here's one, and you can see it's okay, the outputs are probably also nested SegWit, and the input is, it's got both a script sig and a TX witness, right? TX input witness. A sort of pure one is this one, F7, and okay, so you can see oh wait, am I not running? What version am I running? I think I'm running 15.1 still. So I'm not seeing the address. There's a new address format called BEC32, which will turn, see it's 0 and then a pub key hash. Or no, sorry, that's 0 and then a script hash. 0 and then a pub key hash. It says witness version 0 key hash. There's also an address associated with these. I think this version of Bitcoin CLI does not show it, but the new version does. So I think if you guys have version 0.16.0, it'll show, like, here's the address. And then you can see in the input, the single input for this transaction, there's a txin witness. And there's no script sig. There's a script sig field, and it's just empty. There's no actual signature traditionally. There's instead this big thing. Here's the signature, and here's the pub key being revealed. And then it also says, okay, here's the TX ID without the signature, and then here's the hash or witness transaction ID, the hash of the whole thing, including the signature. And they're different, right? Also, you've got size. So this is actually 235 bytes, right? Because you're including the witnesses. And then V size, which is virtual size. This is how big it looks to old software that doesn't know about SegWit. So the new software, this knows about both, right? Okay, the actual size or witness size is 235, V size is 135, 53. So yeah, it's not quite, not a 50, 50%, I don't know. Because this one has 2 outputs, and the outputs don't get any smaller, and the input just gets smaller. And then size, V size, and then you can see what block it's in. Let me get the Coinbase transaction. Yeah. Okay, so the first transaction in the list is going to be the Coinbase transaction, and I can get that one. And okay, so yeah, the Coinbase transaction has a different TXID and hash. Its size is 259, its V size 232. Coinbase has whatever random data they want, and there's the actual output, which is sending to this address, and it's sending 12.79 coins. And then there's this 0 value output. So you can have an output that's got an amount of coins set to 0, it's still okay, and it's got this op return. And the op return starts with AA21, A9, ED, and those 4 bytes mean here's the SegWit commitment, here's the witness commitment to the SegWit transaction hashes, the root of all those. And you have to have that, right, in order to have a valid SegWit block. And so then we can, this is SegWit in action. I think most blocks now will have that. It's also got really, so there was size and V size, right? And that sort of makes sense. But then you have strip, no, V size is not strip size. It's really confusing. And I like, size, weight, height, like what? So size is, I don't actually know. I think size is interpreted the same. This is the actual number of bytes for this block. Weight is you multiply all non-witness bytes by 4, and you leave all witness bytes as weight 1. And that has to be less than 4 million. And you can see here it's just under 4 million. And then stripped size is the size that old nodes see. Yeah, pretty sure. Anyway, so it's kind of confusing. One of the biggest problems in Bitcoin is like names, where it's like, wait, script pub key and like script sig script, like what? Like all these terms and names are just really confusing, and it's sort of getting worse. So yeah, these are not. Also, it's like there's no V size here. I think. Anyway, I think this is actually V size. Anyway, so that's how SegWit works in the actual thing. But it's nice because now you can reliably spend from things before they're confirmed. So SegWit's cool. Fixes malleability, increases the block size. Oh, it does a whole bunch of other stuff too. Okay, so one of the aspects that it fixes, when you're signing a transaction, let's say you have 5 inputs. Each time you sign, you need to hash the whole transaction because it's slightly different, right? You zero out all the signature fields, but on the signature field for the one you're actually signing, you don't zero it out. You put the previous pub key, you put the previous script there. So it's slightly different. It's totally redundant. There's no reason to put it there because it's already in the TXID, but you change things around a little bit. So the idea is, so I'm going to put a signature here. I'm going to put a signature here, put a signature, all 5 of them. Each time I put a signature here, I hash the transaction, right, to get a slightly different thing to sign for each one. It might not jump out at you, but this is actually O(n squared), which is bad, right? Because the idea is, as I extend the number of signatures required in a transaction, the number of inputs in a transaction, the amount of data that needs to be processed goes up with the square of the number of inputs, right? Because I add an input, now the total size of the transaction gets bigger, so each time I sign, I need to take a bigger amount of data through my hash function. Also, the number of signatures gets bigger, or the number of inputs. So this is n squared. It seems fine, right? You never notice, except when you do. So there's like pathological block. There was one like 2015 early in the year where some miner was like, I'm going to make this block that's one giant transaction with like thousands and thousands of inputs. And a lot of software choked on it, and like it took gigs of RAM to process the transaction and things like that. So that was bad. Just in general, if you have a lot of little dust outputs and you're trying to aggregate them into one big, I'm going to have 100 inputs and one output, it takes forever to sign. And it also takes forever to verify. So it's pretty bad. I remember, sort of silly story, Tim Draper's coins. He had all this dust. And it was like nerve-wracking because it was like way more money than I'm going to make in my life, and like moving Tim Draper's coins to somewhere else. And the software by default just swept all the inputs, right, with that wallet controlled. And they were looking at me, they're like, why doesn't this work? Like, is it frozen? I'm like, no, I'm not trying to steal the money, guys. Because he had, like, everyone was sending all these little outputs to Tim Draper's, like, 30,000 coins or whatever, because he was, and then when I tried to spend it, it took like 5 minutes to sign.
When people use P2 pool, the software really struggles with this.
Yeah, so this is, yeah, it's bad, right? Any O(n squared, this is sort of a bug. Segwit actually fixed this. The way they do it is they say, okay, we sort of pre-compute these 3 intermediate hashes, right? Take the whole transaction. This is sort of the global transaction data, and like pre-compute these 3 things. And then for each of the inputs, add another thing, right? Here's this input specific. So this is like global. It's like the hash of all the TXNs, the hash of all the outputs, the hash of this. And then here's the input specific. Input specific, and then hash all these things into one thing, and then sign that. So the idea is it's O(n), in that like you compute these 3, and then you sort of go down, keep changing this for each one. So that saves a lot of time. It's a nice. Oh, you also put in the amount being spent in your signature hash, which is also redundant, right? Because that's committed to in the TXID that you're signing. But it's really nice for hardware wallets, because a lot of times hardware wallets are essentially presented with, here's a hash, sign it. And they, it's a very small system, it's a little chip somewhere. And it doesn't really know too much about Bitcoin. It's just, here's a hash, sign it. Like, okay. And they don't know how much they're spending. So there could be attacks on hardware wallets where they get a hardware wallet to sign something where it's actually moving too much money. So it's nice to be able to like have the actual amount in there. So there's a bunch of stuff like that. It was sort of a giant grab bag of like all these different little fixes, things like that. Fixes malleability. It increases the block size. It does all these other cool things. People didn't like it. Never really understood why.
For all the reasons you've been telling everyone about.
All these reasons? Wait, these seem like good things, right? What?
Well, yeah, but there's some problems with it that could have been made.
Oh, no, that wasn't what. It wasn't like people were like, oh, here's some little things I don't like about it. Because that was what I said. That was like what everyone working on Bitcoin was like. No one was like, thinks it's perfect, right? Everyone's like, oh, but what if this thing is weird? Why'd you do that? Or why didn't you put this in? Kind of things. But no, the people who didn't like it really didn't like it. There's still a bounty on Sipa's head, right? There's, death threats. Someone's like, I'll pay someone to kill this guy. That it's all, this is going to destroy Bitcoin, that, Segwit isn't Bitcoin anymore because there aren't any signatures. It's like, no, the signatures are still committed to, just in a different way, right? You have to build this other tree. So lots of weird conspiracy. I don't know. It became like this really sticking point. And so that sort of led to Bitcoin Cash. The whole idea is like, Segwit is bad. were making Bitcoin Cash, and Bitcoin Cash forked off before SegWit activated in the main network. Interestingly, Bitcoin Cash uses this, so they took a bunch of the code from SegWit because this is a really good signing improvement to signing that Bitcoin Cash used, but they didn't like SegWit. Yeah, I'm still not like, I don't know. There's problems I have with it too, but it's it's an upgrade and it's cool. I think a lot of it was people wanted a hard fork. This was a soft fork, and so there was backwards compatibility, and they wanted to sort of show that people have more control over Bitcoin than they maybe do. It might never be possible to have a hard fork to get everyone on board to like really switch. So who knows? So yeah, it was interesting. It took forever, and that was the last change to the Bitcoin code in terms of like consensus code, and that was it was initially announced late 2015 in Hong Kong. And then all of 2016, it never. So it activated, August of last year, and now you can use it.
People had big interest in stopping it though.
Yeah. There's
coins they were spending hundreds of thousands of dollars a day to stop it from activating.
Yeah. So on Vertcoin, you're like, I'll just take the SegWit code and activate it, and like cool. And then people tried to stop it and spend a lot of money to stop it. I want to say unclear why, because I don't know. It's sort of weird. There's a whole lot of opinions. One theory is that this breaks some mining chips optimizations. One of the optimizations, it doesn't work with a tree of height 2, but if you have a really tall tree, you can swap TXIDs, or you can swap intermediate nodes of the tree, and you'll get a different Merkle root, right? So you can see so it doesn't work here because this has to stay in place, right? But in many cases, the order of the transactions is arbitrary, right? So I could flip these two, it's still valid, right? So what I might do is say, okay, I have this Merkle root, I'm mining, and then I want to flip these two, calculate a different Merkle root and mine. And there were some chips that maybe did this and had these kinds of optimizations. There was also like a patent on it and all this weird stuff going on. It doesn't break, but it essentially loses the optimization if you have this, right? Because you say, okay, I'm going to have this big tree. I'm going to swap something near the top, and I only have to recompute like 2 hashes to get a new Merkle root. However, if I now have this sort of mirror image witness Merkle tree underneath, if I say, okay, I'm going to swap this, I'm also swapping all these, and I have to recompute this. Right? Maybe I can swap some of it, but I have to recompute what this is. This is going to change just as well. And then I have to put that in here, and this is going to be at the bottom. And then I'm going to have to recompute everything all the way up to the Merkle root. So this was called ASIC boost. And then there was a post, Greg Maxwell posted like this sort of like, you guys, like accusatory mail on the mailing list last spring saying, look, we were trying to figure out a way to break ASIC boost, because we think miners have this like patented algorithm that optimizes, and it gives 20-30% speed up, and we're worried that the patents will make one miner have a monopoly and everyone else won't be competitive. So we're trying to think, is there a way we can sort of make software to prevent this from this optimization? And then once they tried to look at it, they're like, oh wait, SegWit does that. We want to make it costly to swap things in the tree. And SegWit does that. Oh, so basically we're good. And then he was like, oh wait, maybe that's why all these people hate SegWit. Maybe this is, these miners who have, billions of dollars worth of equipment with these optimizations in it, which would be rendered, unusable by this new software change. Maybe they're trying to prevent it from activating. It's a theory, and the mining company said, no, that's a bunch of nonsense. Although the way they said it was sort of suspicious. And they're like, yeah, we put circuitry in our chips to do this, but we never used it. It's strange. So who knows? But yeah, that's one theory. I'm not sure how much I believe that's the real reason, but yeah.
Calculate Merkle roots in Bitcoin, why do they not just order all of the transaction IDs by transaction ID?
No, you can't, because the order matters, because when you validate, like, this transaction might create an output that this transaction spends. And so if you swap them, yeah. So if you didn't have intra-block dependencies, then it would all be arbitrary, and you could put in ordering. But there are intra-block dependencies, and so the order does matter. In many cases, it doesn't, right? In many cases, these are two separate transactions. You can swap them. But the software does use the ordering. So yeah, and there's also all sorts of other things that would be better. What I would want is prepend or append the height at each stage of the Merkle tree. That would have helped me out for some things. Because then it's like, since you're at the bottom, just put a 0 at the end of each hash. And then when you get up here, put a 1 at the end of each hash. Easy to, doesn't really change anything. But one problem is, what if I request, so what I want to do in my software, I want to request all the transaction IDs in a block. I don't actually care about the transactions. I just want to see all the TX IDs. The way, like this, right? If I get rid of the head 20, I get giant list of TX IDs. The thing is, and what this will let me do is to look for transactions. If I have a TX ID I know I'm looking for, I say, I'm going to look for it in here. The problem is, what if the person I'm asking is giving me this instead of this? I won't know, right? They all look like random numbers. If I do the Merkle tree algo, I'll get to the Merkle root. It's good, but I don't really know that I'm at the bottom. Unless, it's okay if I'm running a full node and I actually download all the transactions and look and, okay, it works. But to have a way to say, hey, give me a list of all the TX IDs and I can verify that it's correct. I can't do that right now. There's ways around it, but it would have been nice if then they appended a 0 or something. And then, or even all you have to do is just append something at the bottom row or just append the height or something. Then it would have been kind of cool. It would have been easier for me, but oh well. And there's people who've written about this. Yeah.
You say that pool operators are leaving off the wit root, and if so, does it weaken the whole system?
I think what they really do is they just don't support SegWit. So I've seen, especially like on.
They signal for it, so it gets activated, but then they devalue.
Yeah, they say they're going to support it, and then they don't. So they sort of flag their transactions. Yeah, SegWit, and then they haven't actually upgraded their software, so they can't use it. They can't mine it. So you see this a lot on testnet as well. If you're making testnet SegWit transactions, sometimes they just don't get confirmed for a few hours, because all the blocks that come out don't support it, and so they won't use it.
The badly written pool software, if they use SegWit supporting full node with it, it will give them SegWit transactions, and they'll try and include it, but it won't do this. So that
So it's invalid. Yeah, so it's invalid. Yeah.
I guess my question is, does it weaken the security in the system if for 6 months they're not supporting this?
No, it hurts the usability, right? If I want to use a SegWit transact, but as me running a SegWit compatible node, I require signatures. I require all this whole construction. If you make something that looks like it spends a SegWit transaction without this, I just reject it. So security-wise, it's fine. Yes?
I think it might be important to note that the way that these things are designed, and in particular that softwares are designed, is that anyone who doesn't update to the new functionality can't hurt the security of the new functionality. That's sort of that's part of the design process.
Although their security might get hurt, right? Just not a ton, but yeah, if you haven't upgraded, you might see these SegWit transactions, and they look they look weird, but you're like, okay, fine, but you can't actually verify the whole thing, right? You given a invalid and a valid SegWit transaction, the old software can't distinguish, but the new software can.
That's even though the pool operators, there's 6 or 8 key pool operators might not be supporting the wit root side.
If they don't support it, it just, you have to wait until someone that does support it mines the block. So if they try to support it and support it wrong, you ignore them. You don't use their data. You don't use their block.
You just find SegWit transactions stay in the mempool a bit longer.
Yeah. So I think in Bitcoin now it's okay. Testnet's kind of weird, but like there's segwit.party, and you can see what people are doing with SegWit. So yeah, it's about 30. This is by transaction. It's somewhere around 30-something% of the transactions are using SegWit, and then you can see witness size percentage, block size. Okay, so sometimes you got, oh wow, I had no idea. Blocks are way under a megabyte now. Oh, okay, well, free transactions for everyone. You want to use Bitcoin, now's the time. You don't have to pay anything. That looked very different a month ago, where you had a solid red line. You had a sort of, nothing went below 1 million, and then you had a little bit of SegWit stuff going on here. But now you've got like most things are below 1 million. So interesting. Okay, so yeah, so that's the basic idea of SegWit. And if people have any questions, stick around and ask. There's office hours tomorrow at 4 to 6 over there. Look at the homework. And next time I'll talk about Lightning Network payment. I'll try to get into payment channels and see how far we get into Lightning Network stuff.